As we have seen, in case of bipolar sine triangle PWM, the output voltage VAB always varies or always switches between plus VDC and minus VDC. That is why the name bipolar has come. There is an alternate way of switching the same inverter in such a way that we get the same fundamental component. And what is the fundamental component? It is VDC into Vm by V peak into sin omega t. And what are Vm and V peak? Vm is the peak of the sinusoidal modulated signal and Vp is the peak of the triangular carrier signal. What is the other method of switching? This is the other method of switching. Here, instead of one modulating signal, we have two. However, the second modulating signal is just the negative of the first. So, we have MA earlier, now we have minus MA. So, earlier what we were doing? We were switching the legs in a dependent manner. That means, whenever S1 is on, we have also switched S2 on. We didn't have a separate logic for the second leg or leg B. But here, we switch the legs independently. Leg A is switched with the following logic. When MA is greater than CT, that means when one sine is greater than triangle, S1 is on, otherwise S4 is on. For the second leg, leg B, what we do is we compare minus MA against the same triangle, the inverse of the sign, the negative of the sign, with the same triangle. And when that minus MA is greater than CT, top switch of leg B, that is S3 is on. When minus MA is less than CT, S2 is on. So, VBO will not have the negative of VAO, it will have a different waveform. Now, how does it look like? It will look like this. VBO is minus VDC by 2 as long as minus MA is less than the carrier. That is up to this point. And once minus MA becomes more than the carrier, the top switch of leg B is turned on. That means S3 is turned on. So, VBO becomes equal to plus VDC by 2. And then it stays at plus VDC by 2 as long as minus MA is greater than CT. Once minus MA becomes less than the triangular wave, again S3 goes off, S2 comes in. So, the voltage VBO will be minus VDC by 2. So, VAO and VBO will have two different waveforms here. And now what is the load voltage? Load voltage is VAB. And how does it look like? It looks like this third kind of waveform shown here. VAO minus VBO is VAB. And now look at the variation in VAB. It is varying between 0 and VDC only. It is 0 when both are minus VDC by 2. That means both VAO and VBO are minus VDC by 2, it is 0. And when VAO is plus VDC by 2 and VBO is minus VDC by 2, it is VDC, and it will become again 0 because both VAO and VBO are plus VDC by 2, and it goes on. What happens when MA is negative? We can show that when MA is negative, if we follow the same logic of switching, we will see that VAB will have 0 or minus VDC. We will have the values 0 or minus VDC. That means VAB, the load voltage, is having either 0 or plus or 0 or minus, but never plus or minus together. So, in the positive half cycle, it will be varying between 0 and VDC. In the negative half cycle, it will be varying between 0 and minus VDC. That is why this is known as unipolar PWM. However, the average voltage, VBO average over TS, is minus MA by V peak into VDC by 2. That gives us the average value of load voltage over Ts, same as before, same as that with bipolar sine triangle PWM, which is VDC into Vm by V peak into sin omega t. So the bipolar sine triangle PWM, which is shown here, and the unipolar sine triangle PWM, which is shown here, they give the same fundamental component of output voltage. But our objective of this pulse width modulation, as stated earlier, is to do two tasks. One is to accomplish two tasks. One is to get the required fundamental voltage at the output, and also to be able to control the magnitude and frequency of the fundamental voltage. That we have achieved. If you control the magnitude and frequency, or if you control the peak value of the sinusoid MA, the modulating signal, and frequency of the sinusoidal modulating signal, then the fundamental component of output voltage is controlled. That is accomplished. But how about the harmonics? The second objective was to mitigate the harmonics. So how have we achieved harmonic mitigation? In fact, it can be shown that the harmonics present in the waveform of VAB, or the load voltage harmonics, are around the multiples of Fs. And what is Fs? Fs is the frequency of the triangular carrier. There is nothing between the frequency of the triangular carrier and the fundamental component. That means if 50 Hz is the frequency of modulating signal MA and something like 1 kHz is the frequency of carrier, there is no harmonic component present in VAB that is between 50 and 1 kHz. This is a very interesting phenomena, and it can be explained or it can be proved analytically by something called double Fourier series, which is out of the scope of this course. But it can be shown mathematically also that there are no harmonic components present in VAB in between the frequency of modulating signal and the frequency of carrier signal. So if you have a very high frequency carrier, it is always good because our harmonics get pushed to higher frequencies. And why is it good if the harmonic voltages get pushed to higher frequencies? It is because most of the loads in AC circuits are inductive, and when the loads are inductive, what will happen? The inductance will offer certain impedance. And that impedance is frequency dip. So this impedance offered by L depends upon frequency. Let us say VAB has frequencies omega 1, omega 2 and omega 3, for example. So the impedance offered by L will be j omega 1L, j omega 2L and j omega 3L. So the current that flows in this circuit, let us say this is I1, I2, I3. The total current is the sum of the three currents because of superposition principle. Now let us say omega 2 is much larger than omega 1, and of course omega 3 is even larger. Then what will happen? I2 will be much smaller than I1, and I3 will be even smaller. So the fundamental component, let us say if the fundamental component is causing this kind of current, and the currents caused by VAB at omega 2 will be very small, like this, for example. It's higher frequency, so it will be very small like this. And I3 will be even lower. Now of course the average values of these two also will be 0. So the sum of all these three will be almost sinusoid. So this is the advantage of having the harmonics at higher and higher frequencies. Now let us go back to the PWM waveform and see if we can say something about the harmonics. In bipolar sine triangle PWM, VAB has a variation at switching frequency. If you look at this, there is a kind of square wave that is at the switching frequency or at the carrier frequency. So the harmonics are at multiples of Fs. Now look at this unipolar sine triangle PWM. It has twice the variation. The periodicity within Ts, if you just look at this Ts cycle, it looks like VAB has 2 cycles of square waves. So one cycle from here to here, and the other cycle is from here to here. Yeah, here to here and here to here. So intuitively we can say that the harmonics that are present in VAB will be at multiples of 2fs, because there are 2 cycles of this small VAB pulses within one TS, whereas in bipolar there is only one cycle of pulse within the TS. It can also be shown mathematically that the first harmonic after 50 Hz, after fundamental component, appears at 2fs, that means 2 times the carrier frequency in the case of unipolar sine triangle PWM. So that is the advantage of unipolar sine triangle PWM over bipolar. It gives the same fundamental component, but the harmonics are pushed to even higher frequency. So with the same load inductance, your current will be smoother, and we shall see that using an example. In this example, we have considered an RL load, and let us try to look at different ways of switching the same 4 switch single phase inverter or single phase H bridge voltage source inverter, and see how the current waveforms improve with the same value of resistance and inductance. Same RL is used. Now we look at the most simplest way of switching the inverter, that is square wave switching. So S1, S2 are on in the first interval, in this interval from here to here, and S3, S4 are on from here to here, and it goes on. And because it's an RL circuit, the current rise is exponential. That is what is shown here. And similarly, the current fall also will be exponential. And now you look at the harmonic spectrum of VAB. As we know, square wave has all odd harmonics, and that is clearly seen by this harmonic spectrum. What is plotted here? The normalized magnitude of harmonics are plotted, that is VABN by VAB1. So if you just look at the magnitudes, individual magnitudes, they just follow the envelope of 1 by x, and that is what is observed here. And now what we have done, we have switched the switches, or we have turned on and turned off the switches in a different manner, so that this kind of voltage is generated, this kind of voltage VAB. See the second waveform, where the voltage is 0 for some time, and of course plus VDC and minus VDC for some time, and the 0 interval is adjusted such that there are no third harmonic, there is no third harmonic, there is no ninth harmonic, there are no harmonics of the order 3n in this case, and the current waveform looks a little better than that with square wave, as seen from the third figure, the blue color waveform. Now let us look at the harmonic spectrum of VAB. So VAB has fundamental component, that is this, and then VAB does not have third harmonic, and it does not have ninth harmonic, and it does not have 15th harmonic, and so on. Next we have gone a step ahead and calculated the switching angles that are required to nullify harmonics of the order 5n also, in addition to 3n. So 3n components, the magnitude of triple n harmonics will be 0, and also 5n will be 0, right? So with that, voltage VAB looks like this, and then IAB looks a little more better than that we have seen previously. Now how does the harmonic spectrum of VAB look like? It will look like this. It doesn't have third, fifth and ninth, of course. Then it doesn't have 15th. It will not have this 21st. It will not have 25th, and so on. Now the harmonics are fewer, But still you have the 7th harmonic and 11th harmonic, 13th harmonic, and that is why current is not sinusoidal. So instead of calculating the switching angles offline, now we want to do real time PWM. That means switching instants happen on the go. They are not pre-decided. And how is it done? It is done using bipolar sine triangle PWM. So we have a modulating signal shown in the first figure. So this is the modulating signal, and carrier also shown in green color. As you can see, the red color modulating signal has much lower frequency than that of the green color carrier signal. And how does VAB look like? VAB has variations from minus VDC to plus VDC. It is always bipolar. And now the current is much better than what we have seen previously. And why? Because now the harmonics are at even higher frequencies. There is no harmonic between the frequency of the sine wave, this sine wave, and the triangular wave. And that is seen in the spectrum also. See the harmonic spectrum of VAB, we have the first entry here at the frequency F1, and then the immediate entry is at 20th order, around 20th order. Look at this. Even though the magnitude of 20th harmonic is more than the fundamental, our current looks still sinusoidal and dominated by the fundamental component only. Why? Because of the frequency of the harmonic. Because of the frequency of the harmonic, the same inductance is now offering more impedance. So the magnitude of current caused by harmonic voltage is very less. So the total current will look almost sinusoidal. Remember, the value of R and L is kept the same throughout all these switching patterns that we are showing. And the best current waveform is obtained using unipolar sine triangle PWM with the same value of RL. RL is not changed at all. And what is this unipolar sine triangle PWM? Now we have two modulating signals. See, one red color modulating signal, other blue color modulating signal. And the blue color one is just the negative of the red color one. And they both are compared against the common carrier, shown in green color. And leg A and leg B are switched independently. And look at VAB. Now VAB has either variation from 0 and VDC or 0 and minus VDC. Okay, it doesn't fall from VDC to minus VDC anytime. So that is why it is known as unipolar sine triangle PWM. And look at the current waveform. It's the best current waveform that we have seen in this whole discussion. And that is again explained by the harmonic spectrum. The harmonic spectrum of VAB is much cleaner now. The first entry is at the harmonic order 40, which is very far from the fundamental, around 40 actually, and there is nothing in between. So the impedance offered by the inductance is 40 times that offered at the fundamental frequency. So our current is like almost a sinusoid. So this is how we can switch a single phase voltage source inverter in different methods to achieve better and better quality of output voltage and current waveforms.